Thank you, Professor Renati. So the talk I'm presenting today is memory operation by thermal modulation of molybdenum disulfide, MoS2, nanomechanical resonators. So first, a very brief introduction of the material of the device we're using, molybdenum disulfide, MoS2. It is atomic layer material. It's a semiconductor. It's very thin. The single layer could be just 0.7 nanometers. And it's got pretty good on-off ratio when you make it into electronic devices. And it's compatible with other two-dimensional, we call it 2D nanoelectronics. So it's also it have very good mechanical properties that has fairly high Young's modulus, very large string limit. So it's a good candidate for making nano-electromechanical systems, or we call it NEMS systems. So we've been doing a lot of work exploring the nanomechanical properties. Oops, I think this slide has some issue. Here. Oops. We have been doing quite some work regarding this wonderful material. In 2013, in frequency control, we reported the frequency scaling of MoS2 nanomechanical resonators and shows how we can go towards VHF or UHF devices. And we studied the effect of geometric non-ideality on the device performance. In frequency 2014, we leveraged the fact that this device is very thin. It could be as thin as the atomic layer, so it interacts with the environment very strongly. Use this effect to study the air damping of this NEMS resonator and show it can be a very sensitive pressure sensor. In 2015, in MEMS, we reported our exploration of integrating this device, the NEMS resonator, on flexible substrates. And last year in Denver, in frequency control, we studied the temperature effects on the MoS2 NEMS resonator, including the TCF thermal effects and the thermal hysteresis. So here, I want to focus a little bit more on the thermal hysteresis effect. Basically, what we are saying about thermal hysteresis is the frequency of the device, of the NEMS resonator. For example, here, if we switch the frequency, we see the resonance at showing up at a particular frequency. If we change the temperature, as we heat up the device, it's going to follow one path, and if we cool down, it's going to follow a different path back that forms a hysteresis loop. So, and it's quite repeatable and quite sizable, as we can see. The frequency changes a lot, and the hysteresis loop is quite obvious. So there are a few different mechanisms that could contribute to that, and we are doing some experiment trying to fully understand it. But with that said, we're also thinking, what can we use? What can we make use of this hysteresis in these NEMS resonators? It turns out that when we have some hysteretic loop, we can turn that into a memory device. So here I'm going to very briefly illustrate how a hysteresis loop can be leveraged to make a memory operation. For example, suppose this is my device performance. This is the frequency, the resonance frequency of the NEMS resonator. That's the temperature. And this curve, the hysteresis loop, is what the device follows as I change the temperature. Suppose I set the reading temperature somewhere in the middle. It could be room temperature, for example. If I change the history of the device, its thermal history, suppose I heat up first and cool it down, the device will land at this state, which has a higher frequency, which I can read out. I can call this state 1. And if I cool it down and heat it back up to my reading temperature, it's going to land in another state with a different resonance frequency. And it could be another state. We can call it state 0. So what can we use this thing for? There has been a recent rise in the interest of studying thermal circuits with the advent of nano systems. Specifically, people have been trying to make use of the phonon transport as an information carrier to study a few fundamental processes, especially in nanostructures. People have already proposed and tried to study things like thermodiode across this nanowire, which is hard to see, and some thermal transistors based on negative differential thermal conductivity and thermal memories. So basically, people are trying to find analogy of electrical circuits in the so-called phononical circuits. So I'm just going to very briefly mention this thermal memory here. It is a vanadium dioxide nanowire sitting between two heat sources, which control two temperatures. And this material is a phase transition material that when you change the temperature, it's going to go from insulating state to conducting state. And it also has a hysteresis loop. So people are using temperature to switch it between two different states to realize this memory operation. So one challenging of using this nanostructure to do memory operation is that it's very difficult to date to mass produce well-aligned vanadium dioxide nanowires. So this is not a technique that can scale up. So in contrast, our devices, two-dimensional molybdenum disulfide NEMS resonators is a scalable technology because it's two-dimensional nature. The layer structure make it potentially compatible with large-scale operation, fabrication, and IC technology. So here, briefly discuss how we explore our device operations and study these effects. So when we started studying these, we want to quickly prototype a lot of devices, going through many of them to characterize them. So we choose a relatively easy structure that we have a MoS2 crystal exfoliated over a micro trench and form a suspended structure. This way we can quickly produce a lot of devices and study their performances. And we adjust the temperature by putting these device chips. Each small square chip, as you can see here, have millions of device holes on it and can have many flakes on them. And we put them on a Peltier heater and cooler, which allows us to vary the device temperature. And mounted right next to them here is a diode temperature sensor that tells me what the device temperature is. And I can both control the temperature and read out the device temperature using this setup. And we read out the device resonance using an optical driving and optical readout technique, basically using a two laser system. The driving laser is controlled by the output of network analyzer, and the readout signal is fed to the input port of that, and we sweep the frequency and see where the frequency response is, where the resonance is. And I'm going to show you when I apply a series of heating and cooling pulses to the device, how does this hysteresis loop give me memory-like behavior? So this is my data. In this direction, I'm sweeping the frequency. So the resonance of the NEMS device shows up as a sharp peak in the frequency spectrum. As I vary as I go along the time axis, I'm also varying temperature. So as you can see, it's switching back and forth between different states. When I extract the resonance frequency of the device and plot it next to the temperature profile, I'm trying to show you that how this correlates to the hysteresis loop here. And how does the heating and the cooling cycles corresponding to writing 1 and writing 0 operations in a memory device. So we start by reading the device frequency, which is in the initial state with the lower frequency here. We then quickly heat up the device and cool it back down, which is this part. When it comes back, we read the frequency again. It lands up in a high frequency state here at F1. Then I cool down the device and heat it back up, cool down the device, heat back up. And after that, I read the device frequency. It goes back to the lower frequency state. And I can continue, heat, and read. Found it, goes to the high frequency state again, and I can cool again, and found it goes back to the other state. So basically, these two states can be viewed as 1 and 0, which correspond to the high frequency and the low frequency states. Now, this in principle looks pretty good, but one concern that naturally people have is it wouldn't be very convenient if your memory have to be accessed by 2 laser beams. It's not going to be that practical if you want to use it. So we moved forward to use a new device structure, which I'll talk about fabrication a few slides down, where we put electrode contact to device, including a back gate, which is underneath the dielectric, and 2 electrodes contacting the device. So this way, we can still read out the resonance optically, but we can drive the resonance by applying an electrical RF signal directly to the gate of the device. So here shows an example of the device, a monolayer MoS2 flakes suspended over a 2-micron micro trench. And certainly, the measurement setup need to change because now the device is wire bonded. I have to move the temperature sensor close to it. So I also wire bond the temperature sensor on the same die pad as the device and mount the entire package onto the cooling stage, which we saw in the slides before. And here are the raw data of the resonance frequency. It didn't show up very well, but basically in this direction, I'm sweeping frequency. This is my time axis, and you can see the resonance frequency switching between different states. And I'm checking with different laser power and confirm that my laser power isn't affecting the switching behavior I'm seeing in this device. So naturally, it would be nice if the readout can also be done electrically. So here, for this device structure, we can actually realize both electrical actuation and electrical readout. So here's the fabrication process. To keep the molybdenum disulfide flake really clean, we basically start with a trench, prefabricated micro trench, and we transfer the atomic crystal layer directly onto it. Then, instead of using lithography, we use a contact mask such that we don't need to put any resist on the device and evaporate directly through the mask to put contact on it. This way, we can prevent the atomic flake from being collapsed during the wet processing. And we can read out the mechanical resonance electrically using a downmixing technique, which we reported in detail in this MEMS paper earlier. It should be 2016. Apologize for typo. So basically, the resonance, if we tune the phase correctly in one channel, it should show as a sharp dip. And indeed, that's what we observe. Just to make things easier to see, I flipped the vertical axis so a dip shows as a peak in this plot. For this particular device, it's a 3-layer MoS2 resonator over a 3-micron hole. As I change the temperature, we can see it's switching back and forth between different states. And I turn the 3D plot here. I turn the signal amplitude into the color in this 2D color plot, and I extract the resonance frequency at every given moment and plot that together with the temperature profile, which I get from the temperature sensor, and found that it does switch between 2 states, back and forth, with a slightly smaller hysteresis. So in conclusion, we have demonstrated memory-like operation by thermal modulation in MoS2 NAMS resonators. And we tried different devices, different thickness, different sizes, different actuation mechanism, different readout technology. And in the future, we will continue to work on one hand to try to fully understand the origin, the physical principle behind the memory-like operation. And meanwhile, we will try to further push the device engineering to enable fast memory operation. With that said, I would like to acknowledge all the funding agencies supporting this work and thank all my group members, in particular, Dr. Ray Young, the student who worked through most of this project with me, who has recently graduated and will become a postdoc in Stanford. Thank you very much.